So welcome everyone. We're going to make a start shortly. We'll give it a couple more minutes for everybody to join. So welcome everyone. We've still got people joining at the moment, but given as I'm not the star attraction for this webinar, then I think we can make a start. We want to keep to time and keep this within 2 hours. Welcome to our webinar, From Source to Tap, Understanding Where the Water Goes. I'm Alastair Chisholm. I'm Director of Policy here at CIWEM. If you don't know CIWEM, I'm delighted that you found us here. We're a Royal Chartered professional institution, and we represent a community of thousands of water and environmental management professionals and organisations across the world. Our vision is a safer, sustainable world. And part of that vision is a world in which we make more efficient use of our water. And of course, it's far easier to improve performance on issues like water use when you have a clear picture of what that use looks like. The water industry in the UK abstracts 18 billion litres of water every day. Where does that water go? How is the flow through the network monitored? Can this monitoring lead to more efficient usage of water and less wastage? And can it help the industry meet its aspirational goal for halving freshwater abstraction by 2050? For the past 40 years, the number of flow meters on the water network has grown substantially. It's helped to reduce leakage by 1/3 since the mid-90s and suppress customer demand. Recent developments in flow monitoring mean that water losses can be found quicker and pinpointed to specific sectors, properties, and even appliances. This webinar will introduce the methods of flow monitoring used in the water industry and covers an overview of metering, recent research, and a number of up-to-date case studies. But before we get started, there's a few housekeeping issues that I need to run through quickly. Firstly, I'd really like to thank our sponsor, Invenio Systems Limited, for their support of today's event. It's only through generous sponsorship that we're able to bring you these webinars for free. Not only are we bringing this to you live, but it'll also be recorded and uploaded onto our YouTube channel afterwards, so others not able to make it this morning, distracted by homeschooling, the kids, or anything else, can watch it another time. But don't run away. The live experience is so much better. That's because we'll be using Slido to let you ask questions of our speakers today. So if you haven't already, please go to www.slido.com. I think that's 3 W's, not 4. Preferably in a separate browser or on a separate device if you have one, so that you can watch the webinar and ask questions perfectly seamlessly. Once you're in Slido, please use the code source2tap. That's the number 2 in the middle there. You can submit your questions within the Q&A section on Slido at any time during the presentations. And you can also interact with each other, upvote your favorite questions, and comment on any of them within Slido by hitting reply underneath the question. During the panel discussion, we'll be putting the top voted questions to our panel, so please get voting. Please do not use the Zoom chat for your questions to the audience, to the speakers, sorry. If you have any technical issues or you need support from our events team, then the Zoom chat is your tool for that. But as far as subject matter goes, please keep it sat on Slido. The session today is going to be chaired by Mikal Willmott from Severn Trent Water. Mikal, I'm very pleased to say, is a chartered water and environmental manager. He's worked for more than 17 years at Severn Trent, having joined their graduate programme straight from university. Mikal has specialised in water loss management, understanding water demand and flow monitoring. He's passionate about metering and its ability to help optimise water resources. Mikal's been a catalyst for several metering-related research projects and has presented at several national and international conferences. And recently, he's been analysing the impact of COVID-19 on water demand. So without further ado, thank you, Mikal, and over to you.
I'd like to introduce our first presenter. Thank you, Alastair, for that. I'd like to introduce our first presenter today, who is Rob Lawson. Rob is going to introduce or give us an overview of the water resources context. Rob Lawson is the director of Artesia and also the chair of the CIWEM Water Resources Panel. Rob has over 25 years experience in water resource management, including water company planning, environmental studies, water neutrality, investigations, and the assessment of water security. At Artesia, Rob's work has been focused on improving methods for estimating and forecasting customer demand and analysing policy responses to deliver reductions in water use. Rob has a particular interest in water use behaviour and the social science behind this. Rob, over to you.
Hi, Mikal. Hi, everyone. Thanks very much for that introduction. That was great. This is a brilliant event today because it really, for me at least, it goes to the heart of what I'm in this business for. And you can see very clearly from my first slide, if we move on to that. Just take a sec. The clicker's a little bit behind reality, so here we go. Yeah, this is what you'll want to see, a picture of me aged about 18 in my Bruce Springsteen t-shirt doing my undergraduate fieldwork for my dissertation up in the headwaters of the River Severn. And this was heaven for me, really. I'd just seen my first Springsteen gig in 84, 85. And I was standing ankle deep in a beautiful Welsh river measuring flows, and that was something that I wanted to do all my life. And then the slide on the right is just bringing it a bit more up to date. This is the kind of stuff we do at Artesia, where we're trying to understand household water use, and that's a household water meter with a logger on it that's recording very high frequency data that enables us to understand the actual water use in the house in terms of toilet flushing, showers, and so on. So it's measuring water flows of one type or another have been with me throughout my career, and it really is something that energizes me and gets me interested in understanding all those different flows. And crucially, this also addresses the maxim that you can't actually manage what you don't measure. It's a bit of a corny old aphorism that's very popular in management circles, but measuring stuff is fundamental to us actually managing things. And it's interesting to consider where we've come from and where we're at in terms of measuring different water flows. The delay on the clicker is very slow, so we'll start ahead of time. So first of all, I must confess and be clear that this isn't an abstraction. This is the Bellmouth overflow at Ponsticketh Reservoir in just north of where I am in Cardiff, but it's a nice picture, so I thought I'd include it. It's more photogenic than a boring abstraction point. What did we first start measuring? Well, we looked at license abstractions naturally, so that's part of compliance. The second part of what we started to look at was leakage, and this is a very simple diagram of what I know some of the other speakers are going to talk about later on, which is a district metered area system. So that's about dealing with waste and addressing resilience. And then the third point, then perhaps moving on a bit more closer to home, is measuring customer water use. And we're now on a quite big spectrum of measuring customer water use, and I know this is something that Andrew will talk about later in some detail. going from unmeasured customers who don't even have a meter on their supply, and it's still amazing to me that that's the case in the UK in the 21st century, through to dumb meters, a bit like the one in the photograph, AMI meters, where you've got some additional information that you can collect on a more frequent basis, to smart meters, where you've got information coming in from that meter every 15 minutes. And you don't need that logger that I showed you in the last picture. You've got that real-time data from the meter coming in to let you understand exactly what customers are using. So which of these are more important? And sorry, back a slide. Thank you. I'd say they're all equally important. Abstraction's critical. It's about understanding what we take from the environment. That's really, our ultimate impact. It's about the source of every shower and every toilet flush and every washing machine load. And it's something we really need to connect with as a society and as a profession, to understand that all that water that we use in our homes and in businesses everywhere throughout the day, and also the water that's lost through leakage, ultimately comes from the environment. Customer demand, it's about what we do, and it drives what we do as a business. We're about meeting customer demand. It determines the demand patterns over time, diurnally, within the day, but also weekly, particularly weekday to weekend, and annually, as we look at different peaks and troughs within the year, driven mainly by weather. There's also the long-term element to demand. So the classic one I always use is that over the last 30 or 40 years, we've gone from having weekly baths to daily showers. And those sort of fundamental shifts are still going on. We saw last year in the first lockdown that there was a massive increase in demand when many people were at home in some really hot weather. People were out enjoying the water in their garden where they were lucky enough to have one. But it's only now that it's been measured extensively and in detail. And it's not just about the numerical numbers on that dial that you can see there. It's also about understanding customer behavior as well, which I'll come back onto in a bit. And then leakage is also important. It'll always be a necessary evil, leakage. We're never going to get completely to zero leakage, just due to the size of the network and the nature of water. But it's still a waste of money. It's still a waste of energy and carbon, and importantly of social capital. So it's something we need to understand much better and address further. Next slide, please. And these slides here just reflect the importance of those measurements. So top left is PCC over time, and we can see that it rose, as I say, reflecting that change in fundamental behaviour from, say, weekly baths to daily showers from the 60s to the 90s. Fell a bit after the 95 drought, but has started creeping up again over the past few years. So something we need to address. We can also see that leakage reduced from the mid-90s after the drought of 95 in particular, but again has plateaued and perhaps increased a little more recently. And we can see here from the Environment Agency's view of water resources at a national level that there are challenges ahead that we need to address. And it's only by measuring and understanding water use and water abstraction and leakage throughout all of those things I've referred to that we can actually address that. Next slide, please. So what else do we need to think about when we move on to measure and deal with water and measurement of water in the future? Here are a few ideas, and I think and hope that some of these will get picked up through the rest of the session. More and better data analytics, and that's happening at the moment. That's something that Artesia is very, very strong on and does a lot of. And again, like Mikal, we're also working to look at the impact of COVID on demand across the industry. Focus on measuring what matters most. So what is the key thing that will make the difference to understand? Is it peak demand, for example? And also improve the understanding of the water balance. Know where every drop goes. And I think, again, we'll hear more about that in the session to come, particularly around large diameter meters and meters in the upstream network. We need to understand what water's been used for and what drives that use and how this is changing. As I said, big increase in demand last summer or last spring almost because of the pandemic. And is it more outside use becoming a trend, like moving from weekly baths to daily showers? Thanks for your time, and I hope you enjoy the rest of the presentations today.
Thanks a lot, Rob. Thank you for that punchy presentation, a great start, a great foundation for the rest of today's webinar. I'd like to introduce our next speaker now, who's Stuart Trow. He's a director at Invenio Systems Limited. Stuart is a chartered civil engineer and has spent 44 years in the water industry, working mostly on water distribution systems, including 15 years as a manager in a water company and 26 years in various roles as a director of several supply chain companies, currently Invenio Systems and his own consultancy company. He has direct experience and expertise in water distribution systems and as a water loss management from a viewpoint of a water utility, a consultant, a contractor, a regulator, a trainer, a conference organizer, an innovator, and a researcher. He was a member of the steering committee of the first UK National Leakage Initiative that led to the Managing Leakage Reports of 1994, and a member of the team that updated them in 2011. He is a member of the Management Committee of the International Water Association Water Loss Specialist Group. Stuart has been the leakage reviewer for Wicks and Scottish Water since 2010, and he was the Ofwat reporter for Anglian Water from 2009 to 2014. He also advises the board of Welsh Water. Stuart, thanks a lot for being here today, and over to you.
Thanks, Michael. I'll just see if I can take control of the slides. There we go. So, good morning, everyone. The title of the webinar today is Source to Tap, Understanding Where the Water Goes. And that's the purpose of a water distribution system, getting the water from the source works to customers' taps. And in that respect, water is unique as a foodstuff. It's delivered on demand into people's houses. And in these COVID lockdown days, we've all become used to more Amazon deliveries and deliveries from supermarkets and so on. The water industry has been ahead of the game, really, in delivering its product direct to customers. But we maybe are not so good at understanding exactly where that product goes when it leaves the treatment works. We do have meters in the system. We have what we call distribution input meters, DI meters. We have zonal meters on the trunk main system. We have DMA meters as shown here. We have sub-DMA meters, leakage control area meters as well. And then, of course, we have customer meters on households and non-households. I'm aware that we have some people from outside of the UK who have intermittent supplies. I'm talking in the context of a continuous supply here. So why do we need to understand where the water goes? Well, I've categorized these into two blocks. We have an operational need to understand where the water goes, demand and production planning for transferring water between one zone and another, for pump scheduling and so on. And of course, things go wrong in this system. We have events, we have bursts, we have outages of equipment. And during those events, we need to understand how to redistribute the water around the system. And then, as Rob has mentioned, we have to control leakage. We have our find and fix operations, and we have leakage on all elements of the system. And of course, we have to use our meters to charge customers. And then the second block is about regulation and planning, about reporting leakage, about reporting per capita consumption and demand, about understanding water efficiency measures. And we use consumption monitors, either individual household monitors or small areas, or we now starting to use small meters to understand how much water people are using and how much of the demand is due to leakage. Just to emphasize the importance of the regulation aspect, every year Ofwat produces this report, the Service Delivery Report. And if you look in the latest report, it's available online, you'll find this table, which sets out some outcomes on which the water companies are judged. And there are 11 outcomes, 3 of those relate to water distribution, but it's actually 3 out of the 4 water supply requirements, the other one being water quality contacts. So the industry is monitored on leakage performance, the water use, and supply interruptions. So just touching on leakage, I was asked to speak about leakage. There are 2 ways of calculating leakage. The first one is to look at how much water is produced at the supply works, add on any imports from neighbouring companies, take off any exports, and what we left is what we call DI, or distribution system input volume. We then have the measured use to measured households and non-households, for which we require meters, obviously. Then we have unmeasured use, and this is where we have estimates coming in. So that leads to some uncertainty in the top-down estimate. We also have miscellaneous use for our own operations and various other things. And what we're left with after we've deducted those elements is leakage. Then we have the bottom-up estimate of leakage based on minimum night flows in DMAs. And here we have the minimum night flow. We take off the continuously logged users, obviously, again, requiring accurate metering. Then we take off an estimate of the night use, or rather the night consumption, which is the use plus the plumbing losses in individual properties. And that, again, is for households and non-households. And after we've deducted that, we're left with the leakage estimate. Those night use estimates are either based on individual properties or consumption monitor areas, as I've mentioned. And those average values are applied at the DMA level. And I think we might see during the course of the webinar that we maybe shouldn't be applying average levels at DMA level. When this system was first introduced, leakage used to be about 75% of the minimum night flow. But as leakage has been reduced over the last 20, 30 years, it's more like 40 to 50% of the night flow. So, final slide. There are some inaccuracies in this whole process in calculating leakage. There are data inaccuracies of meter under registration, broken meters, missing meters. There's what we call meter lag. Not all of the customer meters are read at the same time, and therefore we have to model the demand from the metered supplies. We have data transfer errors between the meters and the processing and analysis systems. And then we have to question the granularity of AMR data and the type of data that we have. Are we getting live data, or are we getting data which is a little bit out of date? And then, as I've said, we have estimates for unmeasured household, unmeasured non-household, so things like fire supplies, troughs, cemeteries, and so on. And in night use estimates, a key thing at the moment is understanding the split between leakage and consumption. And Rosie Squires from Invenio is going to talk a bit more about the plumbing loss estimates, but also things like distribution system operational use, DSO use, and water taken legally and illegally. That's all based on estimates. So requirement for further metering in the system, more accurate metering, more accurate estimates to get better understanding of leakage and how significant that is in terms of the amount of water that leaves the treatment works. That's me, Michael.
Thanks a lot, Stuart. Thanks a lot. So we've had a look at water resources. We've had a look at water distributions. I'm now going to talk about large diameter meters. And it's something that I've been interested in for a long time. I've worked for Severn Trent for about 17 years. And about 16 years, I've been involved in large diameter metering. Now, what is a large diameter meter? There's no official definition of what a large diameter meter is. Generally, people refer to it as something greater than 250 mils, or definitely something greater than 500 mils in diameter. And so that's 20 inches or larger in diameter. And so we've got a picture here of a large diameter meter in the UK. That's 2,000 mils in diameter. Now, whereabouts would we find these large diameter meters? We generally find them in 4 places. First of all, we may find them at the abstraction point, where we're taking the water out of the groundwater, out of the borehole, or out of the river. We find them often at the edge of treatment work, so just before the water actually goes into distribution. And we generally call this a distribution input meter, or sometimes in other countries, system input volume meter. We find them often on our trunk mains or our transmission mains. These are the large mains that take water to the cities and to the towns. And also we find them on the inlets and the outlets of our service reservoirs. In the UK, we've done some rough estimations, and we reckon for meters that are 500 mils or greater in diameter, each day about 11.25 billion litres a day go through these meters at the edge of our distribution works. If we look at the mega meters then, the meters that are 1,000 mils or greater in diameter, in the UK, we reckon about 3.75 billion litres a day go through these meters. On the larger water utilities, we find that about 2/3 to 4/5 of the water that these utilities put into distribution, put into supply, go through these large meters, these meters that are 500 mils or greater in diameter. We know that large diameter metering is becoming more and more important in the UK. And again, there's a number of reasons why this is. For example, abstraction monitoring. The water companies in the UK are aiming to reduce abstraction by half by 2050. As we lower abstraction, our metering needs to become more accurate, more precise. So again, large meters will have a big role in this. If we look at the amount of water we put into distribution, my understanding is there's an environmental bill going through Parliament that is looking at distribution input targets. So we have targets for leakage, we have targets for per capita consumption, how much water someone uses in a day. We may, going forward, have actual targets for how much water a water company puts into distribution. Also, having accurate distribution input meters is essential for calculating leakage, like Stuart just mentioned, but also for resilient, knowing how resilient your water company is or your catchment area is. Water companies in the UK have to reduce leakage on average by about 15% over the next 5 years. That's quite a heavy task. And what we're seeing now, more companies are looking at reducing leakage on their trunk mains, on their large mains. Thames Water and United Utilities over the last 10 years have kind of shown the way, and other water companies are now following what they've been doing. And this means that we need more meters on the trunk mains and better meters on the trunk mains in order to reduce, or in order to find leaks, to find bursts, and to reduce leakage. In fact, a 2020 UCWI report noted that we needed more and better metering on these large mains. And going forward, we know there's going to be greater interconnection between catchment areas and between water companies. And so there's going to be a greater amount of transfers. And in order to understand how much water is going from one catchment to another, and also from a billing point of view, how much one company is going to charge another company for the water that they're passing over to them, metering and accurate large diameter metering is going to be absolutely key. 2 years ago, Sir James Bevan, the Chief Executive of the Environment Agency, gave a talk at the Waterwise conference. The talk was called Escaping the Jaws of Death. It was quite a wonderful name for a talk. And he said, around 25 years from now, we will not have enough water to supply our needs unless we take action to change. And then in his talk, Sir James Bevan talked about things that needed to happen to ensure that we had enough water. He talked about new reservoirs, new desalination plants, water trading, and reducing leakage. And when we look at all these options of new reservoirs, new desalination plants, water trading, and reducing leakage, all of these will require large diameter metering. So going forward, large diameters metering or meters will become more and more important to the water industry. Here's some pictures of some large diameter meters from around the UK. There's a number of different technologies, and often when these meters are installed, they are in there for a long time. So if you look at the blue meter on the left-hand side, which is an electromagnetic meter, this meter was installed about 30 years ago, and it's still in use today. And it's recorded over 500 billion litres of water. 500 billion litres of water have passed through this meter since it was installed. So these assets are around for a long time, and they're usually put in very strategic locations. There's a number of different technologies that we use. So electromagnetic meters are the most popular large diameter meter we have in the UK, but also clamp-on ultrasonic meters are becoming more and more popular. On a clamp-on ultrasonic meter, you have at least 2 transducers, and they send ultrasound pulses to each other. And how quickly that pulse gets from one transducer to another, you can infer a flow rate from that. And again, we've got wetted ultrasonic meters, and we've got insertion probes. They've got little sensors on their probe, which can kind of indicate what the velocity or what the flow rate is in the pipe. Now, not all meters are as accurate as each other, and where you put a meter can also affect the accuracy. So there's a few things that affect the accuracy of meters. It's worth just very quickly taking you through some of them. The meter technology affects how accurate it is. The meter location, if you put a meter close to a bend or close to a fitting, you may have distorted hydraulics, which will affect the accuracy of the meter. The speed of water or the velocity affects the accuracy of a meter. So really, really low velocities can lead to quite high errors in meters. The size of the pipe, generally speaking, larger pipes or larger meters tend to be a little bit more accurate than smaller meters. The number of measuring points you have on the meter may affect the accuracy. For example, on a clamp-on ultrasonic meter, the more transducers you put on generally improve the accuracy. The age of the meter, the pipe roughness, the water temperature, all these things can affect how accurately the meter records, and also how well it is installed. Not everybody installs as meters as well as they could be. Not everyone looks after them as well as they could be looked after before installation. So again, all these factors can affect how accurate a large diameter meter records. So we've learned a lot about metering over the last 5, 10, 15 years. There's been some really good research by WRC, by Evaluation International, and by other bodies. But going forward, we still need to learn more because these are crucial meters. And last week, NEL announced, along with ARAP and WRC, about a new project they were going to do to look at large diameter metering. And they're hoping to get funds from the Ofwat Innovation Fund. Water companies are also looking at this project, at this research, to see if this will be of value to them. And this is a large project that's going to cost over £1.5 million, and essentially is an umbrella project. It looks at lots of different projects, lots of different research related to large diameter metering. And I'm glad to say that CIWEM are supporting this research. Indeed, the research will give much needed guidance of the design, installation, maintenance and verification of large diameter meters, Alastair wrote in a letter on behalf of CIWEM in November 2020. And there are other bodies also supporting or endorsing this research. So I'm grateful for the opportunity I've had to speak to you today, and just to give you a brief introduction to large diameter meters. We're now going to hand over to Andy Godley from WRC. Let me just give you a little bit of introduction to Andy. Andy is WRC's principal flow measurement specialist and has been involved with flow measurement for over 30 years. His work and his expertise covers all technologies of flow measurement, both open channel and closed pipe, across clean and wastewater applications, as well as domestic and commercial revenue metering. Andy led a major project for UCWER on understanding the accuracy and operation of district meters. Other recent work includes studies on large meter accuracy and the development of uncertainty models and verification strategies for large meters. Andy manages WRC's flow test facilities and has first-hand experience of testing and evaluating the types of meters used for district metering. Andy is an active member on a number of British, European and international standards committees. He is a former member of the National Measurement Systems Flow and Engineering Working Group, which advised the government on investment on flow and engineering metrology. Andy, grateful to have you with us. Over to you.
Okay, thank you, Michael. There's a bit of a lag on this screen, but we should be here soon. So, Stuart introduced the idea of district metered areas in his session, in his slides. And as probably most of you know, these are sort of small, discrete areas of the network, typically sort of 500 to 2,000 properties, with a single feed that can be effectively isolated for a single feed. And the DMA meter is the one that we're using to capture the data, the flow going into that area. My slides aren't moving on. It says I'm controlling them. Oh, there we are. A bit slow. Okay. DMA meters are absolutely an essential part of our metering network. They're used for night flow monitoring. As explained earlier, night flow is critical. So this is the point where demand on the system is at its minimum. So typically between sort of 2 a.m. and 4 a.m., sort of an hour within that period, where legitimate demand is at its lowest. And therefore, we hope that we can pick up leakage from the fact that the flow doesn't go to absolutely zero. We're finding more sophisticated techniques for looking at light flow now, particularly around very high resolution, high frequency logging, which enables very discrete small events within an area to be detected. That's quite important when we start thinking about the type of meters that we want to use in these areas. DMA meters also used obviously for leakage detection, not just from the light flow, but from trends in how that changes over time, control of pressure management systems within those areas, and increasingly as part of a smart networks system. Typically, we're looking here at meters that are 80 to 150 millimeters diameter, so quite a bit smaller than the ones that Michael's just been talking about. And the most common technologies that we find are turbine and electromagnetic meters. A few others that are in use, but the survey that we did for the UK were projects a few years ago showed that, just around about 60% are still mechanical turbine meters, the remainder are electromagnetics, and yeah, the others are just very, very minority types. It's important to understand the workings of the meter, because what we're finding now is that, as Stuart said, leakage has come down, leakage in district areas has come down. We're trying to drive leakage down much more quickly. So we need to be able to find smaller leaks. We need to be able to find those smaller leaks more quickly. And therefore, we need to optimize the performance of our district meters. And to do that, it's important just to sort of have in your mind how some of these meters work. So turbine meters, obviously a technology that's been around for an awfully long time. The water spins a rotor, connects up to a magnet, which then transmits through a magnetic leakage to the register, whether that's electronic or mechanical. Electromagnetic meters, Faraday's law, so you've got a very small voltage generated by a water flow, a conductor through a magnetic field. And what we're seeing, particularly at the moment, electromagnetic meters getting a lot more widely deployed, battery-powered technologies coming through for electromagnetic meters, which are very sensitive. But in order to manage power, in order to reduce cost for these meters, the coils have been much reduced, which means that you've got a much smaller magnetic field, which means that induced voltage is very, very small. And that has implications on how we install the meters. Whichever technology you use, there's various pros and cons for both technologies. Turbines are obviously well trusted, very easy, simple to understand, but they do suffer from sort of long-term mechanical wear, which changes the performance over time. We've had a number of meters through the rig that have been damaged through loss of blades, through blockages, fouling from debris, which obviously has an effect on the accuracy of the meter. Also find that particularly with the mechanical turbine meters, the outputs tend to be limited to a fixed number of pulse values, which if you start looking at very rapid pulse logging, very high resolution pulse logging can be a bit limited. Whereas electromagnetic meters tend to have a lot more flexibility in the outputs and can have integral comms, verification systems, data logging, so you don't necessarily need separate systems for those that you do with the turbine meters. On the downside, obviously, there are slightly higher cost, and also the installation is more critical. And I talked about optimizing performance, and there's various factors that we need to be aware of to optimize that performance. One is the size of the meter. So we need to size the meter accurately in terms of the flow rates we're looking at through that particular DMA. We've mentioned the importance of night flows, and the importance of night flows in able to be to detect the leakage and the night flow allowance that Stuart mentioned. So we need good low flow sensitivity. For all the different types of meters that we have on DMA meters, the meter error, the meter uncertainty is a function of flow rate. So we need to make sure that we're operating in that optimum operating range of the meter as much as we can. So if we get too many low flow points and we're either not registering them or we're getting high errors, typically with a mechanical meter, that will be a severe under recording. With electromagnetic meter, it can be slightly over or under recording, so it's more an uncertainty rather than a fixed error. And obviously, if we get too higher flows, then we can risk damaging the meter. And the graphic on the right is slightly out of date, but sort of shows that not all meters are the same. Even a meter that's the same sort of nominal diameter will have different flow characteristics. So, we need to be very careful in our meter selection to make sure that we're matching the flow characteristics of the meter that we're trying to select to the area that we're trying to monitor. Good installation practice not only helps achieve accurate measurement, but also enhances the reliability of meters. So obviously these meters need to be installed where the pipe is running full, and that's not always obvious. The meter may be at a high point, and you need to be aware that there may be perhaps a bit of air trapped in the top of the meter. So you need to put the meter the right way round for obvious reasons. But particularly with electromagnetic meters, if the electrode is in a point where there's a void, it's not going to measure properly. And similarly with a turbine meter, if the part of the rotor is not submerged, then that changes the hydraulics of the meter and will affect the accuracy. Hydraulic conditions are something that's much debated. you need a good, well-conditioned flow on the entry to the meter, which means putting in upstream diameters, sort of, so the meter, there's a distance between any sort of upstream disturbance, whether that's a bend or a reducer or a valve or whatever, for the flow to develop into what's called a good, fully formed, fully developed hydraulic profile at the entrance to the meter. Some more modern meters say, well, no, you actually need very, very few diameters. There are even some manufacturers that say you need 0 diameters. I would always treat that with a degree of caution. When you go back to thinking about how those meters work, if you imagine that, particularly our turbine, if you've got any swirl in that flow, if the flow is sort of slightly rotating, then that either can accelerate or retard that rotor with respect to what it should be. A lot of modern electromagnetic meters have profiled bores which do a certain amount of flow conditioning, but again, we've tended to find that there is a measurable difference in accuracy or in error, even with fairly modest upstream and downstream lengths. We always also recommend that you don't bury meters. A lot of manufacturers say, oh yeah, you can reduce installation costs, you don't have to build a chamber, you can bury our meter. We really don't think that's a good idea, and I'll explain why in a moment. And with electromagnetic meters in particular, particularly the modern devices that are on the market now, the battery powered devices, then absolutely essential is to get the electromagnetic, the grounding right, the earthing right, whatever you want to call it. As we said earlier in our summary of how these meters work, that induced voltage that the meter is measuring or trying to measure is very, very small. And any stray voltage currents, whether that's induced in the water through nearby electromagnetic fields, whatever, power cables running alongside, all those kind of effects can induce voltage in the water, which can then lead to either an offset or a noisy signal or very poor accuracy at low flow rates. And this is becoming much more of a problem with modern low-powered meters than it used to be in the olden days with the larger meters, the mains-powered meters. And wisdom at the moment, even from the meter manufacturers, is to say, don't rely on earthing electrodes within the meter body, use grounding rings, earthing rings, and ensure that they're all connected up and everything is connected to a common potential to eliminate these stray voltage effects. Short bit on aging and reliability. So, again, when you're making your choice, you want to have a reliable meter. We've done a lot of work on testing turbine meters in particular. And as we've said, they do wear over time, and that will lead to under recording. It would also lead to a loss of low flow sensitivity. And I think the rule of thumb that we came up with was that meters should be replaced about every sort of 10 to 12 years, mechanical turbine meters. If you look at that graph at the bottom, that sort of shows why. So we sort of normalized a lot of data into this, but what that seems to suggest, so the blue bars show the meters, that a proportion of meters that are failing at low flow rates. The red bars are the meters that are starting to fail at higher flow rates. And by fail, I mean give errors outside an acceptable window. So they might still be measuring, but there will be a significant measurement error there. And you can see that sort of when you get to around about that sort of 10 to 12 years, the probability of a meter giving poor performance is around about 50-50. There's so many factors that can induce wear on an individual meter. It's impossible to look at a specific meter and say, well, that meter will have that kind of error after this period of life. It has to be done on a sort of probability basis. So the conclusion we came to was, well, yeah, around about 10 to 12 years is probably the sweet spot for replacing turbine meters. Electromagnetic meters don't tend to have that mechanical wear and damage, but the single biggest source of failure for electromagnetic meters is water ingress, either into the cables, into the cable gland, the terminal box, the coil assembly. As soon as you get water into the coils, it starts shorting the coils, changing the magnetic field and giving you an error in measurement. And partly that's why we say don't bury the meters. Some soils can be highly corrosive and water permeating through the soil, particularly if it comes from road runoff, can contain salt, contain diesel, all sorts of things, quite nasty, that will lead to long-term corrosion of some of these electrical parts. And that will then impact on the measurement performance and ultimately lead to meter failure. So there are a few other things there. Don't join cables. Cable joints are susceptible to water ingress. Stress on cables and cable glands. So don't lower the meter into the chamber by the cable. Seems fairly obvious, but people do it. I've seen people do it. It stresses the cable gland, stresses that seal, and then over time that will lead to water ingress. So in summary, very quick run through there of DMA meters. They're absolutely essential to good network, good leakage management from the point of view of night flows, leakage trends, pressure management, so forth. So they need to be looked after. You need to choose carefully and make sure you've got the most appropriate meter, the most appropriate type of meter, size of meter for the flow rates that you're expecting, the outputs for whatever system you're feeding that data into. And to optimize performance and reliability, good installation practice is absolutely essential from the point of view of hydraulic conditions, so the water flow through the meter, with electromagnetic meters, particularly modern ones, the grounding, and as I say, the last point there, mechanical meters will wear, and they're not fit and forget, so you have to maintain them, you have to replace them on a fairly regular interval. And I think that's all I really wanted to say, really, at this point. So hand back to Mikal. Thank you.
Thank you, Andy. Thanks for that wonderful presentation. And some of the work that WRC did with Upqueer a few years ago now, is something that we'll be using in Severn Trent, is helping us with our good asset management in replacing DMA meters as soon as we need to replace them. So very grateful for the work that WRC and Upqueer have done. Just before we go to Chris Rees, before I introduce Chris, just to remind you that if you want to put some questions, please go to www.slido.com. I went to Slido for the first time this morning. Very easy to find via Google. And then you type in, and it's really obvious in Slido where you need to type this in, #source2tap, and you'll be able to then ask questions to our panelists. And we've got 2 more presentations until we get to our Q&A. So I'd really encourage you to ask those questions. We've had some real good expertise here this morning. Let's put our panelists to work. Let's ask them some real good and difficult questions. I'm going to be chairing that Q&A, so I can make sure that I don't get any of the difficult questions, but I'll pass out all the difficult questions to others. We're just going to, I'm just now going to introduce Chris Rees. Chris joined Welsh Water in January 2018 and is currently Leakage Strategy Manager, specialising in the areas of leakage, demand management and asset strategy. He has 15 years experience in the water industry as a contractor, consultant, and now within a water company. He has led on the delivery of programmes of work across both potable and wastewater networks, working with most of the UK's water companies. Chris studied accountancy and management at Cardiff Business School and entered into the water industry following graduation. Chris, thank you, and over to you.
Thanks very much, Michael. Delighted to be joining colleagues from the UK and across the world today to talk about the DMA element of water accounting, specifically covering off leakage and night use, estimations which go into the leakage calculation. Let's see if I can control the slides. So not to be in competition with Rob, but he did show a nice photograph of Ponstic Reservoir, and that's actually Alwyn Reservoir in North Wales. Thank you. So consumption estimation within DMAs has been well developed over the past 25 years since, well, I mentioned earlier with Stuart and his colleagues who developed the management leakage guidance in 1994. But we've had to reevaluate these assessments due to the introduction in part of the consistency of reported measures guidance, which requires companies to apply specific as opposed to industry average data when estimating leakage, but also due to the increased rate at which we need to reduce leakage. Ofwat challenge water companies to commit to a 15% reduction over AMP7, and that is far beyond the sustainable economic level for many. So in order to achieve these reductions efficiently, we need to gain a greater understanding of where leakage is occurring. So this is something that Stuart did touch upon from a slightly different angle earlier on. I thought I would cover the components of DMA leakage estimation for those who may be unfamiliar with this. So DMAs are usually made up of an inflow meter and outflow meters, which are logged at 15-minute intervals to provide a balance of consumption in the area. We then assess leakage during a night flow window, which is shown on the screen here. As Andy mentioned, when demand is at its lowest, and so error is minimized. An assessment of night use for both domestic and non-domestic properties is made, and then the remainder we estimate as leakage. So a greater understanding, I guess, of the household night use and non-household night use estimate means that our accuracy of the leakage estimate increases, and so we can deploy our leakage resource more efficiently. So I'll just go through first off the non-household night use element of this. So methods are developed, I guess, over the years for estimating night use. I know Rob and guys at Artesia have done a lot of work on this, as you spoke about earlier, and we've sort of night use for each user type is predicted as a sort of logarithmic function of daily consumption. But that data historically has come from sort of small login samples. But what we've kind of moved on to is a model where all the non-households are grouped into 14 user groups, which is largely based on standard industry classifications, and further divided into 5 consumption bands. What that produces for us is a requirement of around a sample of 1,000 permanently monitored sites. So from that sample, we can dynamically adjust our night use allowances for days of the week and seasons, making our assessment of leakage far more accurate in the present day. So that's kind of moving from an annual average and company average allowance to a lot more specific per DMA and adjusted weekly. So you can see from the graphs there on the screen how important it is. When you consider normal demand patterns of sectors such as education, agriculture and tourism. Previously, the graph on the slide show the impact of COVID isolation restrictions on day and night use. So education, for example, on the top left there, exhibiting a normal kind of weekday, weekend profile before the lockdown. So you can see the kind of spikes and drops between weekday and weekend. And then when lockdown kicks in during March, you can see that the daily flow, total daily flow is kind of dropped right off, but night use has stayed the same. So that's kind of indicative of urinals and plumbing losses really. So if we were to have used the annual spill volume estimate in this instance, we'd probably be under recording that night use quite significantly. So just touching upon meter penetration, whilst all non-households are metered in the UK, it's not true for domestic meters. So low water companies, and there's a lot of interest in smart metering at the moment, and lots of embarking on big metering programs which span many investment periods. There's a need to understand domestic consumption now, and with our situation of only having 50% meter penetration, we needed to look at alternate technologies to try and model what was going on in those unmetered customers. So in terms of the household night use, we've got 2 methods of assessing household night use. First takes small DMAs, small area monitors, of which we have a representative sample of about 150, and the flow meter is logged at a very high resolution to count each pulse of the meter. The information is then fed into our leakage reporting system, WaterNet, which analyses the very lowest flow rate to deduce the night use. So this method allows us to update allowances again on a monthly basis, so it accounts for changes in demand seasonally. The second method, which I'll go into a bit more detail on, is where we log each property with a temperature sensor, meaning we can monitor both metered and unmetered properties cover 100% of the DMA, as opposed to the 50% which is currently metered. You see just a little bit about how we deploy the stopwatch logger from Invenio, and I'm sure Rosie will speak a bit about this coming up, but we kind of do a pre-survey where we clean out stop taps, make sure we locate every connection point to the main, and then deploy the stopwatch temperature logger within the chamber there, and then the data gets fed back through the cloud into an analytical engine, which Invenio and the team have developed over the last few years to convert the temperature measurement to a measurement of flow. And apologies for the clarity of these graphs, but it's kind of showing the granular detail of the temperature measurement there. So the different demand profiles are kind of indicative of normal use for the leak, continuous use. Just flicking on to the next slide. You can actually pick up in that top one there, and this is coming from a further study where we followed up the customer. They had a small flush every 30 minutes, so you can see the kind of temperature variation occurring on quite a regular basis every 30 minutes there. And then the bottom one with a large continuous flow, so effectively the temperature is following the ambient temperature quite well there. On the next slide. So this one's really interesting for us in the leakage prevention. So the slide shows an aggregation of stopwatch data together with a total line in the sky blue compared to the DMA flow meter. So as well as attaining our household net use, which is the black line, you can also identify customer side leakage, which is the blue line, and then the remainder being a far lower estimate of network leakage than we would have had first imagined. So in this instance, we can tailor our approach. So whereas we would have deployed leakage inspectors on the network, we can deploy our Project Cartref program, which targets customer side losses and high use. So really getting into the efficiencies there of where we would have been chasing network leakage, which doesn't actually exist. And we can also note there at the top of the graph during the daily profile is a gap between the stopwatch data, where we'd had a logger on each connection point, and what the flow meter is telling us, and that's kind of indicative of an unknown connection. So not necessarily illegal use, but the connection to the system that we are not currently aware of our metering. So we actually did follow that up and noticed there was a secondary connection to an industrial unit. So it's a byproduct, I guess, of this analysis. So this graph then is of network leakage and increasing our understanding of that. So this is all areas where we've deployed the stopwatch across Welsh water, and it is really indicative of how a flat night use assessment probably isn't correct, because there's such a big span of consumption and background leakage. So it really has given us granular level of detail to know what intervention to use in which DMA. Now kind of builds up to the next slide. Animation didn't quite work there. So this slide shows our current estimate of distribution leakage. The studies have redefined their understanding of customer side losses and increased their estimates to almost 25% of total loss. And it's also reduced the quantity of water that we estimate as background losses. I'm sure as technology like we spoke about today and metering technology develops, this understanding of background leakage will develop further. And yeah, I'm really excited to kind of redefine what we class as background leakage in our journey to zero leakage, I suppose, for the future. Then just a final slide on what we're kind of doing about it, and I touched upon Project Cartref earlier. Whereas we sort of, in the leakage drive over the last 20 or so years have concentrated a lot of effort on the distribution side. This redefined understanding of where our leakage is occurring has led to the formation of Project Cartref. So this is where we look at areas of high customer side loss, undertake a deployment of the stopwatch logger to really understand where that's happening. And then we can undertake a targeted program on those customers which have got high losses, and also from a water efficiency perspective on those exceptionally large users. And we're kind of seeing, where we've got meter customers, it's quite well known that the demand spread is quite narrow, whereas for unmetered customers, it's very wide. And in some cases, we've got users kind of using 4 to 5 times the average, and it's those users that we can target with water efficiency campaigns and messaging to try and reduce that. And going back to Stuart's kind of point of the leakage and demand being key measures from Ofwat, we can tackle both of those with this project. That's a bit of a whistle-stop tour, I guess, of how we have increased our understanding of non-domestic and domestic demand in our night use and leakage calculation at DME. But if you do have any questions, please let me know.
Brilliant.
Thanks, Michael.
Brilliant. Thank you, Chris. And it's great to see the use of technology, and relatively new technology as well, to find where those leaks are and where maybe high usage is, and to go after the high users as well. I was in Cape Town a couple of years ago, where the Cape Town government essentially kind of looked at high users, and that really helped them reduce the demand and the water they were abstracting. So thank you very much, Chris. We're going to stay with Welsh Water now, and we're going to hear from Beth Parker. So Beth Parker is a water resource scientist at Welsh Water. Previously, she has worked within Welsh Water as a water resource technician and has 6 years experience in private water treatment, leading global projects to provide cleanup of contaminated water. In her current role, Beth undertakes water resources modelling to assess the resilience of Welsh Water's water supply system to dry weather, informing operational decisions and strategic investment. So Beth, over to you.
Hello, good morning. Thanks for the introduction. So I'm here to talk to you about how we take all of that leakage data and input it into water resource models. So hopefully the slide will change. I don't think it's working. Can somebody change the slide for me, please? Thank you. So I'm going to talk to you about allocating and aggregating demand data into a water resource model. So what is demand data allocation into water resource modeling? So water resource modeling allows a mimic of reality in terms of a water resource demand zone. That includes the water resource asset, which might be a river, borehole, reservoir, the water treatment works, and a breakdown of the demand centres into a simple representation of the network. This allows us to test climate change scenarios, seasonal demand changes, and test the resilience of these networks. It also allows us to reflect operational changes within the networks and the reduction in leakage that Chris was previously speaking about. It also allows us to test our deployable output, or DO, from our water resource zones, which is a good test of how resilient we are to changes in supply. So how do we do this? We utilize the data that our leakage team collects from the DMAs, and we utilize XDMAs, which are a larger allocation of DMAs, super district meter areas, and reference those into demand centers, which we then allocate into our models to allow us to represent demand changes seasonably and over the course of the demand data collection. We utilize an application called A2D2, which is a purpose-built application allowing us to take this data into account and review it and allocate it to our models. Previous to this, we were utilizing a mass balance system to allocate demand. This was thought of as not the most accurate representation and didn't allow us to have changing demand profiles and run different scenarios based on demand outputs in individual years. So moving on, I'm going to show you through the process of how this works. So I'm hoping that the next slide will come up. There we go. Okay, so this is a leakage network schematic of a zone in West Wales called Mid and South Ceredigion. It's a fairly rural zone. The most nearby town would be Lampeter, if anyone's aware of that. And it has two sides to the water resource zone, one which is a river extraction and a water treatment works, and the other which is two reservoir extractions and a water treatment works. So the way that we allocate demand is using these pre-existing network schematics. We allocate demand based on geography, ensuring that constraints are represented, which may cause us to split demand centers into further detail, and representing rezones, which is where you can supply one area of the network from one water treatment works or another, depending on the asset stress of the water resource. As you can see, the SDMAs are the colored lines within the leakage network schematic. And there are 40 SDMAs within this water resource zone. However, to allocate for demand and to make it simpler for the model to run, because there's a lot of data to run into the model, we've turned this into a simpler representation. If you look at the top right side of the drawing, you will see three demand centers, which is the gray, pink, and orange. And if somebody could click next for me, I think it's my slide doesn't seem to be working. Originally, this was split up into two, a grey and an orange zone, but there's a particular area of this trunk main here which can be rezoned off the water treatment work supplied by the reservoirs and onto a river. So we wanted to represent that, and in discussions with operations, if somebody can click next for me, we should represent that we made this a bit more granular by turning this into three demand centers, which allows us to represent the rezones in the model more accurately. So if the next slide can come up, this is what it turns into. So this is an Aquator schematic. Aquator is a water resource modeling piece of software, and it allows us to simplify the water resource zone into water treatment works, demand centers, our water resource assets, such as reservoirs or rivers, and any constraints in between. And so you can see those 40 SDMAs in the previous network schematic turned into 7 demand centers. These are areas of key supply, rezone, or between assets and constraints, which allow us to represent the water resource network as best as possible, and then allocate the SDMA demand into these individual yellow dots you can see within the network. And if you look at the right side of this, you can see the 3 demand centers, Strata North, Ross, and Strata South, were those represented on the previous schematic, which we went from 2 to 3. The simple representation here is not because we're going down the data, it's because we're trying to ensure that the model runs as smoothly as possible with the large amount of data that we have to input for our scenario runs. So when we're doing climate change runs and looking at stochastic drought scenarios, we have 20,000 years worth of data, and so the model has to be a simple representation of the network with enough detail to allow us to represent constraints and ensure that our DO that we produce is accurate, as well as be able to take in all of that data. So if the next slide, please. So after we've allocated all of our SDMAs into our demand centers, we then utilize A2D2 to allocate demand. So the way that A2D2 works is it takes into account our reference allocation, and it looks at the demand data that our leakage team has collected, and it creates profiles which factor up and down the demand based upon seasonal changes. So if you look at the graph on the left, you can see Strata North is a demand center with 7 SDMAs in it, and those different colorful lines are the different SDMAs in the profile and how they change over the year selected here, which is 2013. At the base of that, you can also see a couple of straight lines, and these are the upstream demands, which A2D2 also includes and allocates based upon the percentage take up of the demand within the total water resource zone of this demand center. On the right-hand side, you can then see that profile turn from 7 SDMAs into 1 profile, taking into account the averages and peaks. This profile is then input into our Aquator model to change the demand based on the seasonality of this particular demand center. For example, you can see here that there's peaks in August and there's peaks in around Easter time, which can be associated with tourism. But in other zones where we have, for example, students returning, the demand can differ. And so it allows us the analysis of that profile to ensure that we're looking at an accurate representation of this specific demand center and these SDMAs. And as you can see, the highest demand can often come in dry weather. And when we're testing drought scenarios in our models, it's very important to have this high demand come up at a time where our resources may be stressed to allow us to properly test the ability and resilience of our water resource zones. Next slide, please. So the final step is to allocate the demand amounts, and A2D2 allows us to look at a long-term average of distribution input split by our reference allocation or our demand center setups. So in Mid and South Carolina, we have 7 demand center setups, and it splits the allocation by the number of SDMAs and the amount of demand they take in each of the demand centers and allocates a percentage. We then utilize this number to allocate a demand amount to each of our demand centers in the model, and this is what is ramped up and down those demand profiles we showed you on the previous page to give a accurate changing demand profile over a year of demand within the zone. Next slide, please. So then we input this data into Aquator. And Aquator is a water resource model software, as I previously described. So here in this graph, you can see water treatment works operations. So this is the 2 water treatment works within the Mid and South zone. At the top on the green line, you have a very spiky line, which is the realistic actual data of 2018 throughput of the water treatment works. And the more straight line is the weekly demand data that is produced by A2D2 and is from the water treatment works in that model. And then at the base, you can see the 2 blue lines are the other water treatment works in the zone represented for 2018 and the model data. So what you can see here is the test that we've undertaken to ensure that our total allocated demand to these water treatment works is an accurate representation. So we want to check that the peaks are the right height and that the troughs are the right height. So in the bottom, you'll see that the water treatment works drops in flow and the top water treatment works increases in flow respectively. And that's due to the fact that we can rezone in this network and take pressure off the reservoirs, which are more resource constrained than the river. You might notice some differences between the 2 profiles in terms of the actual data and the model data. That's because we're looking at a model result of a dry year and 2018. So the weather isn't exactly the same. But what we want to check here is that we have the same real world volumes and that accuracy is occurring with the peaks and troughs. So next slide, please. So just a final overview of how this process is undertaken. So an allocation of demand is triggered, whether that be the build of a model, a water resources management plan, or drought plan, network changes in dry weather, or operational incidents and planned works. This leads us to engage with our operational teams, our leakage teams, and our distribution teams to ensure that we've got the correct allocation within our models. We then allocate SDMAs and TDMAs, TDMAs being trunk district meter areas, to demand centers for our model. We design our Aquator demand centers and we use A2D2 to set up the demand. And then we do the Aquator behavioral analysis review, which is what you saw on the previous slide. If all is well and it's accepted, then we go with the demand and we begin scenario testing. However, the benefit of utilizing A2D2 is that if for some reason the data doesn't appear correct in the model, we can go back into the demand and analyze it. We can change our allocation by engaging with operational teams and review the process. So it's by all means not a static process, and it shouldn't be a static process. As Chris explained in the previous presentation, we have targets to reduce leakage, and that allows our demand data to change on an annual basis. We get new demand data, which we can input into the A2D2 and run different scenarios, different years, and change our input. So if we go to the next slide, please. So you can see here in this graph, this is a long-term profile of Mid and South Carolina demand. And you can see that the demand is has been increasing since 2011 when we first started utilizing this data, when we first took in this data for A2D2. So this allows us to analyze our long-term profiles and have a look at the changes over time. A2D2 is, it gives us these benefits. We now use collated QA'd meter data from the leakage team, whereas previous mass balance data was not an accurate representation of the network and didn't use real world data. We can add other demand inputs, such as non-households, unmetered customers, large customers, leakage and upstream losses. We can analyze individual years and anomalies and take into account where network changes may have occurred and changed the data set we use to either model a scenario previous than that or after that. It creates an easy input for modeling. So our models can take the direct output of A2D2 as an upload. And so there's no need to change or set up the data. And it allows annual inputs and changes as demand data changes over time. And we get more granular in our network and SDMAs. Allocations may change, and so it allows us to assess those and take into account the record of changes. And as I said, it also takes into account the changes in leakage and the changes in demand stresses. So 2020 was a particularly busy year in terms of demand. In spring, we saw some of the highest demands we've seen in a while, and also some of the driest weather. And so by utilizing this application, we can take into account that change in demand and model scenarios such as this. So thank you very much. That's me. And I have got a slide that says any questions, but I'll leave that to Slido.
Thank you, Beth. I think the presentations we've seen today have kind of reminded us about the importance, and best presentation there, we're talking about rivers and reservoirs, about the importance that we have to look after our supply and look after the natural environment. Pardon me. And also we need to kind of meet customers' demands as well. And we've spoken a lot about trying to reduce leakage and about the importance of also managing the network so we can optimize the water we have. So I'm just going to go to Slido, and we've got a few questions on there. So thank you for all those that have gone to Slido and put the questions. We have a question that is for Rob Lawson, actually. Rob's not here, and it's about demand patterns and changes in demand patterns due to domestic waste recycling. I'm going to actually hold on to that question, and we're going to do that at our next Q&A, because we've got a couple of presentations in a few moments' time that look at water efficiency. So I've got a question that perhaps I'll come to you first on this one, Stuart. It says, with domestic customers having no option to switch water company, do the presenters think that reducing leakage will depend mainly on regulatory control at stroke penalties, rather than companies improving their performance for other reasons, e.g. to try to gain customers? You're in many ways have played a role in the regulatory regime. Stuart, wondering what your thoughts are on that question.
I've just seen the question, Mike, and it's a very good one. I think the main driver at the moment is meeting the regulatory targets from Ofwat, the 15% reduction challenge in the ODIs, the penalties and rewards that go with that, and balancing that off against the same issue for PCC, for consumption. It's going to be a tough challenge for the water companies. So I think the main driver is regulatory, but I also think that none of the companies want to be bottom of the table when it comes to leakage. It's bad PR, it's bad for reputation. And it also affects the customers' attitudes towards that company when it comes to things like CMEX score as well. So yeah, it's a good question. I think the main driver is regulatory, but I think there's also customer perception of the company comes into it as well.
Thank you, Stuart. And I'd encourage all those panelists that have presented, if you want to put your cameras on so we can see you, because there's maybe some questions coming your way. Anybody else wanted to comment on that, on what Stuart said?
I think probably the other thing to build on that, Michael, is as well as all the points Stuart made, was just around the kind of headroom and future water resources. Leakage and demand management is a key part of that, and from what Bethany showed there in her future modelling, the more we can do to reduce leakage and demand gives us that headroom to meet the future challenges, I suppose, of society with changing water use, changing industrial use, and also population growth. Yeah,
absolutely. And I know in Severn Trent we often talk about leakage as being a bellwether. Meaning that obviously what we do on leakage gets reported into the press, and it's something that customers seem to be very interested in on that. So again, it's a very important thing. And again, as you say, Chris, we talked about kind of lowering abstraction, and we have this kind of aspiration as a water industry to halve the freshwater abstraction by 2050. And again, leakage plays a massive, massive role in being able to do that. Okay, Andy, there's a couple of questions here for you. At the bottom here, can meters be used on pipes with reverse flows, Andy? And if so, can the meter determine which direction the flow is going?
Yeah, most of the meters that are available these days, particularly the turbine electromagnetic, will potentially have dual outputs, either forward and reverse, either separately or through a flag to indicate reverse direction. I suppose the one caveat around that is electromagnetic meters are inherently bidirectional and will work equally accurately in either direction. Some of the turbine meters will have a slightly poorer performance in the reverse flow direction. But yeah, the answer to the question is yes and yes.
Brilliant. Okay, we're going to ask a question about climate change in a second, but there's another question for you, Andy. So while you're here, we'll keep you on it. This is from Kevin Murray. He says, Andy, for DMA meters, will some of the new inline ultrasonic meters be a useful comparison between, or a useful compromise, sorry, between turbine and EM meters?
Yeah, a few years ago, we tested one particular sort of small piece ultrasonic meter, and it gave very, very good performance. I think it was sort of slightly let down by reliability, but the actual measurement accuracy was very good. And I'm aware that there are a number of these new meters that are coming through, sort of partly designed for revenue applications, but also in slightly bigger sizes for network meters. And yeah, they could work very well. Ones we've tested on at sort of revenue meter, i.e. the small ones, have given very good performance. My one concern, I think, is around whether they will be sort of, I'm just trying to think how to put this without going into too much technical detail, but I think the measurement principle for ultrasonics is well established, as you said yourself in your thing on large meters. They provide an attractive option, and some of the smaller ones give very good performance. There are a couple of concerns around sampling intervals with battery-powered meters and around potentially robustness, where they use effectively reflectors within the flow to get an axial transmission of the ultrasound along the flow, so you've got something intruding into the flow. Now they don't all work like that, so perhaps there's a bit of finessing around that answer. But yes, I think the answer is essentially it's something worth looking at. We're about to start testing one, I think, for in the near future. So it'd be interesting to see how well they do work.
Okay, thank you. I think that was a broad yes. Given the speed at which water demand pressures and climate change are occurring, and the long lead in time for the construction of large infrastructural projects, what interim measures are being implemented to reduce potential pressure points in the network? Is there anybody that would like to answer that? It's a great question, because it does take a long time sometimes to do some of these infrastructure projects. Are there things that we can do in the interim that will help us look after our water resources, perhaps improve measurement?
I think just quickly, the leakage and demand management is something we can do now, and I think that's why we're setting ourselves challenging targets, is to allow us to give us that headroom really until these larger infrastructure projects can be realised.
I think that's a great answer, and I think there's a lot of products that we can put into the network that retrofit. So we've just seen from Welsh Water where they put in the Invenio Stop.Watch. Again, that's a product they can put onto the stop tap of all their customers. We've also seen in DMAs where they put a lot of sensors, a lot of water companies in the UK have now put tens and tens of thousands of sensors to pick up the noise of leaks, so they can find leaks a lot quicker through acoustic logging. You look at a lot of the metering that is now being installed, say on the large diameter meters, a lot of retrofit meters, such as the clamp-on ultrasonics or the wetted ultrasonics or the insertion probes. So a lot of the technology out there is retrofit technology, because it does take a long time. It does take a lot of planning permission to get a new reservoir or to build pipes so you can transfer from one catchment to another catchment. So Absolutely. I think there's a lot of the technology is based to do retrofitting. Well, we're just going to finish on this Q&A part at the moment, and just thank you for all those panelists that have provided answers and given an excellent presentation. We are going to take a super quick break. We're just going to have a 3-minute break, a comfort break, so get yourself a very quick cup of tea or a drink or whatever, and then we'll be back at 10:57 to hear 2 more presentations and again a few more Q&As. Thank you. Welcome back to this CIWEM webinar. I'm now glad to introduce our next speaker, who's Andrew Tucker. He's our little celebrity. He's our bit of stardust we have today. He was on Radio 4 later last year, or towards the end of last year, talking about leaky loos. And Andrew is the Demand Reduction Strategy Manager at Thames Water and is responsible for strategic direction of water savings through metering, water efficiency, and customer engagement. He was previously Thames Water Head of Water Efficiency. Key responsibilities include delivering the business water efficiency targets across London and Thames Valley. He is overseeing the development and delivery of multiple initiatives on household and business customers, delivered in parallel with Thames Water's smart metering rollout even, and as a large-scale bespoke demand management initiative. Areas of work include large-scale in-home retrofitting, smart water metering, business and schools and water efficiency communications, retail propositions, online tools, customer advice, and delivering demand reduction targets. It's good to have you today, Andrew, and over to you.
Thanks very much, Michael. Can everyone hear me?
Yes, we can.
Awesome. Okay, I'll get cracking now. I'm desperately hoping that my mouse has control. Yes, it does. Thank you. Okay. So I want to get cracking straight away and talk about bringing it down from the strategic level, the network level, which was everyone has been talking about, down to property level, and looking at households and then water efficiency. This animation illustrates our rollout of a compulsory metering program. We are installing smart meters. They are AMI, so advanced meter infrastructure. So we have a series of masks across London, almost similar to a mobile phone type of mask setup, and we are getting hourly data reads back from our customers. We are rolling out, we've been doing this for about 5 years, and it's going to keep on going for quite some time yet, given the scale of our audience. We have about 10 million people, about 3.75 million homes in our supply area. So it's a big, big challenge. That information comes back, and we've really developed our own sort of in-house analytical capabilities to take data to insight to action. And the action is the field-based action of fixing leaks, helping people with water efficiency and demand reduction. We're doing that through a Power BI dashboards plus analytics behind the scene. Big things that come from this is that, quite simply, smart metering is a complete game changer for us and for the rest of the water sector. We've got about 480,000 odd smart meters in the ground in London. We'll add an extra over 600,000 over the course of this AMP period, which is 2020 to 2025. And whereas previously we were maybe getting a million and a half meter reads a year through the old manual reads, we're now getting over 11 million meter reads a day. So it's water company turning into big data company. And it changes the perspective of what we do. We now understand wastage better, which is internal plumbing loss. We're identifying our leaks better, and we're understanding customer usage. And I can tell you now, all those three things, usage, wastage, and leakage, smart meter data is rewriting what we understand about that. Usage is incredibly variable. We're seeing households that are less than 20 litres per property per day to households next door or across the road that are over 35,000 litres. So the focus on an average number is sometimes a little bit fraught due to the sheer range of it. About 13% of all homes that we're seeing in London constantly flow. It's little leaks mostly, which I'll show you. About 9% of total unmeasured household usage is from wastage, so leaky loos and dripping taps. So it's a massive issue for us to go for. Okay, I want to talk about quickly COVID impacts, because we're often talking about what COVID is doing. We are understanding what a new normal is going to be when it comes to household and business water consumption. Although Rob Lawson has left the call, he and his team at Artesia are doing the big piece of work looking at the COVID impacts on water consumption across the entire sector. Here's a snapshot of what's happening within Thames. This one here is actually in London. Quite simply, the black line here is water consumption in smart meter households in London. The blue line is the same consumption, but last year, sorry, when I say last year, I mean 2019, which is a typically normal sort of year, if you're going to have a normal year. And it's broken down into like a per occupant. We've done the per occupant sort of metric here, and the x-axis is the weeks along the year. And what we're seeing is large spikes. So what COVID is essentially doing is more people are at home, so business usage is coming down, household usage is going up. We don't have the perfect household average, all households are increasing by 15 or 20%. We don't yet have that number. We need to get through a bit of a seasonal approach, but we are seeing spikes in the early days of COVID of between 10 and 60% increase in consumption. That was a spike. So what COVID is effectively doing, instead of having typical weekday and weekend usage, it's like now having 7 days of weekends. And what it does on a hot day is it really amplifies those spikes when people are outside using water and hoses, sprinklers, paddling pools, etc. And what we're seeing on the right-hand side of the graph there, even in wet weather, cold wet weather we've had over the last few months, that delta, that increase in above normal consumption is a result of COVID with people being at home. Whilst we don't have the same level of meter granularity in our Thames Valley region, we're seeing the same sort of thing, but actually potentially even more extreme. When people move out of their flats in London and think, I actually don't need to be here now because I'm working remotely, I'll go and live somewhere else. And that's exactly what we think we're seeing in the data. We will get more meters into this area over time, but the information we're seeing at the moment is COVID is genuinely having a significant impact to household consumption. Every region is different. Okay, we've talked, a number of us have mentioned the term PCC or per capita consumption, and it's embedded in our water company targets. It's in national frameworks now. It's a metric that's used fairly well around the world, but we've actually embedded it now actually in target, and we're seeing it's probably not the best metric to do that. Quite simply, even though we've seen that the average person uses 143 or 141 litres a day, they absolutely do not use that as the average. Smart meter data actually improves our understanding of what consumption is actually like. So if you look at the total average, and this is a histogram based on customers that we've put a smart meter in the ground, we're seeing good granular information, accurate information about their consumption. And whilst the black line there, that is our average, our PCC that we would report at the moment, about 146, the most common usage across all of our customers is probably closer to 100 litres per person per day. The vast majority of the customers use less than what we classify nationally as that PCC average number. So the consumption numbers of PCC we're showing now is greatly skewed by a smaller number of very, very high usage households, either through occupancy, just their general behaviours, their garden size, affluence, or leakage, wastage, sorry. Things like leaky loos is really contributing to this. So it's something for us to watch going forward, but it really shows that the PCC metric is going to be impacted by COVID. We're getting better understanding with smart meters, and it's probably not a very good metric to use for these things going forward. So we just need to keep that in mind. What the smart meter data is showing us is really granular information about usage and leakage. The top stuff there, those drips there, is a breakdown of wastage and customer side leakage. And we've seen that the vast majority, there's the scale of those big drops there, I apologize for my bad graphical design capabilities, are really, really small flows. We have a huge number of households with lots of little flows, dripping taps, leaky loos, maybe a little leak on a seal somewhere. And when you scroll back down, on the bottom part of the graph, that's the breakdown of typical household consumption. That's not PCC, that's total household consumption. And you see the majority of people fall in this 100 to 500 litres per house per day. Now that's really important because it shows that that smaller number on the right-hand side is skewing that PCC average metric. We have a very, very large water efficiency program at Thames. We've been doing it for quite a while. But the main thing I want to show here is linking it back to data, smart meter data. Historically, we've been going into people's homes. We've been going into sort of 50 to 70,000 homes a year in the previous asset management period. We've brought that down now, whereas previously we had almost like a battalion of people going through broadsword areas and helping everyone who possibly can get to with water efficiency. Smart meter data enables us to pinpoint. So that big battalion has turned into a bit of a special forces unit, and we're now better targeting households that are either using more water or losing more water through wastage. So it's better bang for buck, and that graph shows our conversion of an old smarter home visit, a water efficiency retrofit, and sort of behavior change advice visit. In the black is how much water we would save historically when we did that. The green shows us converting during times of COVID, focusing on high usage households, but using a virtual visit because we couldn't get to the homes for a while. And we're actually doing that right now because of the current levels of COVID lockdown. So we're conducting those visits over the phone and video call if the customer is okay with that. The blue shows us when we do get back into homes, on high usage households, the bang for buck is better. So smart data has actually enabled us to about double or more than double the amount of water we save per water efficiency intervention. So huge, huge positive for us. Smart data has enabled us to explore new things. So we're going a bit more innovative here, and we're now using smart meter data with customers registering for a group called Green Redeem, and it's essentially gamifying the data to reward them with non-financial incentives. So we give people through Green Redeem points based on their consumption, their weekly measured consumption against their own baseline sort of usage. And if they save water this week, they get points, and they can use those points on things like prize draws, shopping discounts and charity donations, because the points have a value. The cool thing is it enables interaction about water efficiency, where historically it's very, very difficult. So we want to get more people, more smart meter customers onto this thing and benefit it in the same way they might get points from different loyalty cards. Why not get points from saving water and be rewarded by it? And constantly talking about it and then reading their proactive emails puts water efficiency and demand reduction on their mind, as opposed to maybe once a year get it. So energy efficiency they know about. Let's do this thing to get water efficiency on the same level of awareness. Leak or lose, finishing up now. Huge amount of work has been done with this. All of our teams going into homes and businesses, hundreds of thousands of visits we've done over recent years. We've been collecting the data about leak or lose, understanding what parts are failing, what brands, why is it failing, is it what materials, is it what designs. We've been taking videos, photos, and taking all the failed parts that we've replaced to gain a real understanding. We're using that understanding, that insight, to engage with the manufacturing industry, and we're now working together with them to try and come up with solutions to completely engineer this problem out of existence going forward. We've still got 29 million homes out there might be suffering it. On a household level, we know that around 5% of the households will have a leaky loo. It's about 1 in 20. The average leaky loo is about 400 litres a day. That's the equivalent, or if more than the total, an average family's total daily consumption. So it's a big, big thing to go for. And it's typically a 50-50 split between the seal of the drop valve and the seals in the inlet valve. So bad materials, not so great design. And as I said, that's what we're trying to work with the industry to improve. In businesses, you'll see more businesses with the leaky loos, quite simply because two things: more toilets per site, and they're often not driven to go and save that thing. It may not be their fundamental driver. But big thing going forward. It's had a lot of press recently. We're certainly playing our part because we want to completely fix this thing. Michael, back to you.
Brilliant. Thank you, Andrew. I saw that little thing right at the end there about costing the earth. That's still available on BBC Sounds if anybody wants to listen to it, where Andrew helps us understand about the leaky loos problem. Excellent documentary by Radio 4. Okay, our final speaker for today is Rosie. And Rosie has been working in the water industry for 5 years. After graduating university with a chemical and processing engineering degree, she joined Invenio Systems and has progressed as the company has developed. Now working as a project manager and client manager for the Southeast region, she has worked with many water companies across the UK, specialising in targeting leakage and in high nightline DMAs using Invenio Systems Stop.Watch technology. So, Rosie, over to you. Rosie, you're still on mute. We can't hear you.
Thank you, Michael. So, can you hear me?
We can hear you. I've lost where your slides are.
Yeah.
Oh, brilliant. There they are.
Thank you. Right. Thank you, Michael, for the introduction. So I'm basically just going to talk briefly about what we do in Invenio Systems, and also a study that we conducted in 2019 that was about plumbing losses and just how prevalent they are across the UK. So, next slide, please. Thank you. So Invenio Systems started about 5.5, 6 years ago. It came about by the directors having the idea to use temperature instead of the traditional acoustic methods for leakage detection. So it works under the principle of you have the temperature of the water in the vein and the temperature in the surrounding ground, and every time there is a use event, you pour water through that. So we started off with some dumb loggers that we deployed to customer stop taps, and we could do various approaches of a blanket approach to an area or individual targeted properties. We've now started to go into more communicating loggers, and deploying them in different places throughout the network to try and look at more network-sided leakage. But it's just trying to find out different appliances for this new way of looking at leakage. So we put the loggers out, we collect them in, and then we analyze that data. We've got hundreds of thousands of data sets from this now, and we have a machine learning algorithm that learns from the data that we feed in and link it back to analyze it, run through the scripts, and produce a result on whether there is a continuous flow at that property. And also we can get use and a few other different factors from that data. So next slide. So these are just a few examples of that data. I won't go into too much detail, but so basically we've got the top is just classic use. If you imagine, so you've got that water drawing in from the main, you get a spike down to that water temperature, and then you gradually rise up. If that property or commercial business has a continuous flow past that point, then it will never return back to that ground temperature, and you will have basically the temperature of the water in the main is the temperature in that stop tap, because it's constantly drawing water through. So there's a couple of different profiles with varying of the size of different leaks, but that's the standard procedure, and so we can log individual supplies and get that data back, whether they're metered or unmetered. Next slide. So if you imagine a tree and branch kind of system, so if you've got your DMA meter on the inlet, and then you have branching off into different residential streets and individual supplies, some of them will be metered, some of them won't. But if you blanket approach on every supply you can in that area, you can get demand profiles from each property and also pinpoint the locations of those continuous flows. So you get the amount of leakage in that area on the customer side. You also get the night use from each individual property that you have logged. So you can add those up, you can have their demand and add it up, and then the rest is inferred network leakage. So if we look on this graph on the left, if you get the DMA flow data from the 15-minute profile, you get the 15-minute accumulated data from each supply, you try and match them up, there will be a gap between the two. So that's initially the continuous leaks. So if you move that up for the customer side use that you've also calculated, then what is remaining should be anything that is not accounted for in this survey that Rees mentioned earlier, or network leakage. So it's just trying to really account for everything that's going on in that area. Next slide. So customer side leakage is split usually into two different types of leakage. You have underground supply pipe leakage and internal plumbing losses or wastage leaks. So an underground supply pipe leakage, usually you can hear it from the stop tap, whether you get your metal pipes or you get your plastic pipes. As traditional leakage methods are usually acoustic, and metal is a lot better to transmit sound across. When it is metal, you're more likely to hear that noise on that stopcock. If it's plastic, that can reduce the likelihood of you hearing that. And also, if that length of the supply is longer, it can also mean that you struggle for that. And then you have your wastage leaks or internal plumbing losses, which are even further away and of course have different manners around that leakage. So they vary in size quite a lot, and they can be a lot harder to detect with traditional leakage methods on that outside stopcock. So for this study, next slide, please. So plumbing losses can be of various different types of leaks. They can be different from dripping taps to leaking boilers to leaky loos. So as Andrew was saying a second ago, there's quite a bit of information around leaky loos now. If you just do a quick Google search, you can bring up a lot of information on that. And from the BBC article that went around last year, lots of people are starting to cotton on how common this is. And anyone that has the push button toilets, I would very much recommend you to look at your toilet and just see if you have that dripping leak down the back of the toilet bowl, because it's very easy to miss finding it, but it is very common to be there. So we should, so what are we actually doing to target these leaks? Because if you imagine a leaking cistern, that has a bowl or a tank of water that it's draining from. And when that level gets below a certain point, it triggers a flush and you get an extra draw of water from that stop tap or OSV, whether it's metered or not. So traditional methods, that does not look like a continuous flow from a technician on site, because it'll look like a use event on a traditional meter. And also you won't have that noise on that stop tap. So if we go on to the next slide. So from our stopwatch data, we've got a few 100,000 pieces of data from properties throughout the UK now. Plumbing losses can take a different manner of forms. So if you look on the diagram on the left, that example that I was just talking about of draining that, it being a tank that's draining constantly, but only when it triggers a certain level, you get that that use event going through. We can see that in our data. We call them regular peaks because it basically looks like use events at a regular period of time. So this can vary from every 5 minutes to every hour, but it happens all throughout the data at night time and during the day. And so from that, we can indicate that that is likely a plumbing loss and that is where you want to look. So a different example is just the graph on the right. So that's a continuous flow going throughout. So that's a continuous draw of water through that stopcock. So that could be a supply pipe leak or a wastage leak. And all we need to do is just clip on a temperature sensor as close to the water as possible on a bit of pipe, which the usual access point, the easiest bit, is just on that boundary box or stop tap. Next slide. So we've done a number of studies already throughout the UK looking into plumbing losses and underground supply pipe leaks. So the size of plumbing loss that we found is varying between 0.8 and 3 litres a second in that plumbing loss, not litres a second, litres per property per hour. So we wanted to do another study throughout the UK to just try and narrow that down figure and do a more up-to-date study. Next slide. So we took a sample of properties throughout 4 different water companies with 1,250 properties each. We've tried to bias the selection on the age of the houses just to try and get a good distribution throughout and see if the age of properties has an effect on that leakage. Next slide. So the results from that operational study with logging on stopwatch data came out with a plumbing loss figure of 1.4 litres per property per hour, and an average of 12% of unmeasured households have a plumbing loss at any time. So from Andrew's slide, it's good to see that he's getting 13%. So we pretty much agree from that study that a large number of households do have plumbing losses, so we should do a lot more to target plumbing losses throughout. And the age of properties does have an effect on those results. So the older the property, the more likely you are to have a plumbing loss. Next slide. So there was two sides of the Uckwheel plumbing loss study. So we had that operational side where we did 1,250 properties per area. We also got some smart metered data from 4 different water companies. So we got that data from them and analysed it to look at the leak alarms on that data. And from that, it showed that more properties had a smaller leak than a larger leak. And so, as agreeing with Andrew, that you're more likely to have a smaller leak than a larger one, and we should really focus on those properties. Next slide. So, breaking that into the different types of plumbing losses. So we have the most common from those unmeasured households were 5% of properties did have a toilet leak. And then we're just showing that the plumbing losses from the Uckwheel report, which is the same figure than the 1994 leakage report, is it used a figure of 0.5 litres per property per hour, and we're saying that's 0.9 higher. So we really think we should target them and do more to look out for plumbing losses. Thanks, Michael.
Thank you, Rosie. And so Rosie's the final presentation that we've got. And I think what you've seen is we've gone really have from source to tap, understanding how we monitor the water usage. And I think what's come out from the last few years from the smart meter work that we've seen down in Thames Water and across other water companies. And again, what we've seen from Invenio and the work that they've done over the last 5-6 years is that there is a lot more plumbing losses, a lot more wastage than we expected. So that's been a real useful insight. And again, that helps water companies understand where they need to focus resources on that. So if we just bring up some of the Slido questions, I'll take you through them. And we're going to use the one that, or the first question we're going to ask is the question that was actually for Rob Lawson originally, but we're going to pass this over to Andrew in his role and his involvement with water efficiency. And so the question is, Andrew, with the changing patterns of demand observed over the years, such as from baths to showers, has anything been observed since the increase in domestic waste recycling and these themes?
It's a great, unique question. I don't know if there's anything different around the increase in domestic waste recycling. I'm assuming that we're talking about, probably just a qualification, the question, is it waste recycling of?
I think it's talking about that.
Yeah, just, you know, recycling has grown in prominence, I guess, over the past decade. And, you know, I just find myself rinsing out the yogurt pot quite recently, and it's a new demand for water. Okay. So just, if, you know, down to micro-component level, whether we could sort of see that.
Yeah. So when we've gone the micro-component studies, and there are a number out there. We've also been collecting a lot of huge volumes of data around micro-components, but based on customer usage of our online calculator. When we've gone into people's homes to do our retrofit and behavior change programs, we capture all that on the tablet devices that our staff are using with our own customer engagement tool. And it shows that whilst I'm not going to try and pin something directly on the waste recycling and the rinsing thing, we know very, very accurately when you average it out what proportion of household usage goes to toilets and showers and baths. Baths and showers is the largest chunk now, but the biggest variable there you're seeing is taps. And taps will have, you know, a shower has one use, toilet has one use, taps will have 10, 15 different uses. So your rinsing of things for waste and recycling is part of that. You've got really different cooking usage now between different ethnic groups and different demographics. That adds to the variability of the tap use. So that element there is probably the greatest unknown when it comes to domestic water consumption. But what we're seeing now is with more people staying at home, working from home, that non-household balance has shifted. It seems to be, based on our stuff so far, probably increasing everything.
Okay, thank you.
Yeah, could be a potential study of the future.
Okay, we'll stick with you for a second, Andrew. So a couple of questions about kind of the long tail that we've got, that we saw in your data, these about 3% of customers, or maybe a little bit higher, that are using more than 500 litres a day and things like that, or households. Yep. Is that primarily, is that wastage, or is that actual usage?
Haven't got the perfect answer for that now, but I haven't got the perfect answer to give you a percentage of usage versus wastage, but it's predominantly usage.
Okay.
Wastage will be part of it. The biggest chunk of that, from what we've seen so far, is usage.
Okay, brilliant. And also, since COVID-19 and lots of offices are not being used now in London, yep, and things like that, have we seen consumption in London fall?
So rather than the term consumption, I would say distribution input. So the total amount of water that's been put into that network for that covers London, since COVID, that is lower than what you would normally see. So you've got a high proportion of businesses. An element of those have stopped operating. Some of them are in lockdown or reduced operation. And then coupled with that, you've got a proportion of households, flats, probably single occupancy flats, that are no longer being occupied. So what the water companies would call voids, you can actually see that the actual number of voids has actually increased during the COVID time. So the total amount of water put into London has decreased. The balance between household and non-household has changed, and will continue to change. We need to keep learning. The total amount of demand that we're seeing in outside of London has increased. But with discussions across other water companies, it's almost as if every different water resource zone is different. There's no one perfect answer for this, but depending on the proportion of agriculture, the proportion of businesses, proportion of large flat detached households with bigger gardens, you almost have to treat it as a case-by-case basis. But for us, London has decreased a bit, Thames Valley has increased.
Okay, and that there's some logic to that, and you touched on that logic in your presentation when you think of kind of properties and the size of the properties and garden size and things like that. If the panelists are okay, we're meant to finish here, but if you're okay to go on for another 3 or 4 minutes, there's a couple of questions that we've got. Andy Godley, got a couple of questions for you, if that's okay. 2 questions. First of all, has WRC tested the impact of water conductivity and mineral deposits on electrodes for electromagnetic meters? And also another question about what's the minimum pipe size you'd consider using an ultrasonic meter on rather than an EM meter, and what criteria would you use, kind of a clamp-on meter or an insertion meter in front of an electromagnetic meter? So a couple of questions there for you, Andy.
Okay, so the conductivity question, I think there was some work done on conductivity quite a number of years ago, and I think what the conclusion was that for most network applications, certainly in the water distribution network, conductivity isn't a problem. I mean, very, very low conductivity waters can affect electromagnetic meters, but that you don't generally get very low conductivity in a water distribution network. So generally not a problem. I did hear of some problems with some very low conductivity upland waters on abstraction for raw water use, but I think that's fairly unusual, especially with modern technology. So I don't think conductivity is a particular issue with using mag meters in water supply. The other half of that question was around mineral deposits, wasn't it? Not specifically, I think, is the answer to that. We haven't specifically looked at mineral deposits on electrodes. Again, the fact that we haven't looked at it suggests that it's not a huge problem. We've done some work around fouling on electrodes, but typically, again, wastewater applications where fouling is more grease, fat, that type of thing, which, yeah, will disrupt the signal path and will disrupt the measurement. Moving on to the ultrasonic one, I guess the thing with ultrasonic flow meters is they come in a number of different formats. So you can get the clamp-on type that you mentioned. You can get the type that actually, like our insertion transducers that go through the pipe wall, through a tapping in the pipe wall and connect directly with the flow. Or you can get the sort of spool piece type, which are, you know, built assembly with the transducers in, and obviously, you know, the cost of those and the relative cost and ease of installation will depend on a number of different factors, including the number of paths that you've got. So that's quite a difficult question to answer. I mean, what I would say is that, you know, the more paths, the better. And I think your work with Evaluation International has shown this, Michael, in that if you can get multi-path ultrasonics rather than single-path ultrasonics, then you'll certainly get an improvement in accuracy. Wetted transducer types, spool piece types will be more accurate than clamp-on types because you've got a number of variables taken out of the equation, number of uncertainties in terms of pipe material, pipe wall thickness, or all the rest of that taken out of the equation. So yeah, multipath. If you want to optimize accuracy with ultrasonics, then you need to be looking at, you know, multipath and contact transducers, whether they are insertion or whether they are sort of spool piece types. And again, that will depend on size. So very, very large ones will tend to be insertion, and as you come down smaller, then you can get the spool piece types. But again, you know, the insertion ones have the benefit that you can hot tap them into a live main rather than having to disrupt the main. So, you know, there's a whole sort of plethora of issues to cover there. So it's not necessarily quite a straightforward answer. But
yeah, I think most independent specialists would put an electromagnetic meter in if they could, but it's hard to put those in. It's hard to retrofit them because of the difficulties that you have. And as you said, Andy, more transducers tends to lead to greater accuracy. I know one company who put in 16 transducers earlier this year on one of their really large mains. They wanted high accuracy and they couldn't put in an electromagnetic meter. Probably the last question for kind of all our panelists here is just to talk about kind of the variability. So we know a lot more kind of the work that Rosie's talked about, the work that we've seen in Welsh Water, the work that Andrew's talked about with smart meters and with all the different sensors now that we can use. What does that teach us about the variability of night use? And what does that teach us about operational leakage and how we do leakage operations? Rosie, I'm wondering if you've got a thought on that.
Yes, definitely. So from the studies that we've done on different areas throughout the UK, we find that night use can vary a lot between different areas. Sometimes it is interesting knowing the type of the area as well, because if you're more a city centre DMA, then it can tend to have higher night use, and the profile from the district meter, you can read a lot from that. And also leakage varies a lot throughout the UK. So even though I've said an average plumbing loss figure, it can vary a lot from DMA to DMA.
Anyone else want to kind of talk about the variability in night use and how that may affect operational leakage?
Yeah, I'll jump in really quickly. So the insight that we've gained over recent years from smart meter data on households has given us a better understanding of usage. So we now know that, and from that understanding of usage in London in particular, the place doesn't stop. There's usage all the way through, and far more than we had previously allocated into the equations that went into leakage versus usage and so forth, which you know, night use is a component of. So we've actually had to shift the time period in which, I mean, other companies are the same, shift the time period at which you use to determine your night use. Usage is far more variable depending on each different factors such as demographics and ethnicity, time of year, seasonality. It's just crazy. When it comes to the leakage operations, we've now seen that where previously this much was allocated to the leakage world and this much to the wastage world, smart meter data shows us that ratio is almost the other way around. So understanding that greater granularity and accuracy of water balance means that you can better apportion where that water is actually going. So better than we've ever been before. And the thing it has on leakage operations is two things. One, better targeting of locations. So customer side leakage and even sort of DMA leakage, the more points of interest you've got there generating data back, the more accurate you've got as location. And the second one there is better balance. So understanding that equation when it comes to annual reporting, we now know where water is going and being lost and used better than we have before, and that needs to continue. So that my leave here is basically more smart metering is the key to leakage and usage.
And Stuart, you've been a pioneer in this area. About 6-7 years ago, you said we're using more water than we think we are, you know, and you were one of the first to say this in the UK, in the world perhaps. So can you just give us a 1-minute overview of your thoughts and then we'll wrap up?
Yeah, it came about when Aquia started to talk about zero leakage, and we had a workshop in London where the subject of background leakage came up, but no one really understood what this thing is called background leakage. And over the last 6 or 7 years, with the work that we've been doing with Invenio and the work that Thames have picked up from their smart metering program, we found that night use in DMAs varies considerably, and plumbing loss in DMAs varies considerably. So if you just take the minimum night flow and take up a standard allowance for night consumption, then you'll have the wrong level of leakage in that DMA. And I'm convinced now that companies are over-reporting leakage in some of these, what they consider to be high leakage DMAs. And they're actually wasting money going out looking for leakage that doesn't exist or it doesn't exist on their network. It might exist inside the customer's properties. So I start to worry about, these ambitious leakage targets. We've got a 15% reduction this AMP, but talk about a halving leakage, getting down to 10% or even down to zero leakage. If that leakage is not where we think it is, then we won't achieve those targets, and that will have implications for water resources and supply-demand balance. So I do think that the industry needs to look very closely at this thing called background leakage and get a better understanding of it.
And I think where we are now compared to where we were 5 years ago, Stuart, through kind of some of the technologies we've talked about today, through the smart water metering and by having these discussions on these webinars, I think we're a lot far more forward than we were 5, 6 years ago. And so we know a lot more. So thank you to all the panelists today for kind of your input. Thank you to kind of you, the audience, who've helped us with the questions, who've come. We really appreciate it. We love doing these little webinars. We kind of learn so much from each other. I'd like, on behalf, also, I'd like to kind of thank CIWEM for supporting this event, for Alastair and Emma and the team in the background that have made this come together. I'd like to thank Invenio, who've sponsored this event today. And without the sponsorship, CIWEM wouldn't be able to hold these free webinars. I'd also ask you on behalf of CIWEM that shortly after this webinar, you will get an email, a little feedback form. Would encourage you to fill that in. Those feedback forms do make a difference. So today we had a bit more question and answer time than we otherwise would have, and that's because of feedback we got from other forums like this. So please do send that feedback in. It does get listened to and things do change as a result of that. Also, please look out for other CIWEM events that will be running in the next month or so. Not least the best practice in climate change adaptation reporting, which is a webinar that's going to take place on the 24th of February. And again, on behalf of CIWEM, thank you for attending today and have an absolute great day and stay safe. Goodbye.